Hello everybody. Today we're going to talk about 1.1, the logic of geometry. So the first thing we're going to do is we're going to talk about some reasoning strategies and some definitions that are going to help us to build these logical arguments that we're going to need in geometry. So the first two, deductive reasoning and inductive reasoning, go together. Deductive reasoning is general to specific logic, and then inductive reasoning goes the opposite way. Inductive reasoning is specific, I can't spell, specific to general logic. So an example of deductive reasoning would be, say you know what a dog is. You know a dog is an animal with 4 legs and a tail, and it barks. So if you come across an animal and it has 4 legs and a tail and it's barking at you, then you can pretty safely assume that that animal is probably a dog. All right, that's your general reason. You have a general picture in your mind of what a dog looks like, and you can apply it to the specific situation where you can see an animal and decide whether that animal is a dog. Inductive reasoning happens more often when we're doing science, when we say, all right, I am performing an experiment and I'm going to draw a conclusion from that experiment. So if you decide to flip a coin 100 times and it comes up heads 50 times and it comes up tails 50 times, then you can say, I believe that if I flip a coin, I'll get heads 50% of the time and tails 50% of the time. So you're using inductive reasoning to make that conclusion. The next 3 pieces go together. A definition, a theorem, and a postulate are all statements that you can use to show a logical argument. So you can use a definition to say, I'm going to get from this piece of information that I know to this piece of information that must be true because of this definition, or because of this theorem, or because of this postulate. So a definition, it states the meaning of a term. So it states the meaning of a term. Right? We all know what a definition is. A theorem is more mathematical. A theorem is a mathematical statement that can be proved. And being able to be proved is a big thing in geometry. So it's a mathematical statement that can be proved. All right, and then in contrast to a theorem, a postulate is the opposite. A postulate is an unproved assumption. An unproved assumption. So these are important because we can use postulates and theorems and definitions to format our logical arguments in geometry. There is one main difference of them, though, with how they can be used. So a definition is always reversible. So I'm going to put that here. Always reversible. That means that if you have a definition, you can use it both ways. So say the definition is a square is a parallelogram with 4 equal sides and 4 right angles. We can use that forward. We can say, all right, we know something is a square, so we know these things about it. We know that it has 4 right angles and 4 equal sides. Or you can go the other way, and you can say, I have this thing, and it's got 4 equal sides and 4 right angles, so I'm going to say it's a square. So I'm going to go from backwards to forwards and say that that definition can be reversed and still be true. Theorems and postulates, however, those are not always reversible. Not always reversible. Sometimes they are, but sometimes they're not. So if I say that if it rains, I will wear a raincoat, that is a statement that works forward, because if it rains, I will wear a raincoat. But if I turn it around and say, if I wear a raincoat, it will rain, that no longer makes sense. So that is not reversible. So you always have to check to see whether your statements that you're using are reversible and whether they could be used for another purpose because they are reversible. The next vocab word here is conditional statement. And conditional statements are what we're going to be using most today. A conditional statement is an if-then statement. So an if, ... then ... statement. All right. Conditional statements have a hypothesis and a conclusion. The if is the hypothesis, the then is the conclusion. So they include a hypothesis and a conclusion. We'll do a lot with conditional statements today. And then finally, we've got the chain rule. And the chain rule is one of the ways that we can link our conditional statements together. So we can say, if, we'll write this in symbolic notation. If A, then B. If A happens, then B will happen. And another statement might be, if B, then C. If I study well, I will get good grades. If I get good grades, then I will go to college. So that middle term, if I get good grades, is the same with both of my statements. That means that according to the chain rule, I can take those two statements and smush them together. And now my new statement is, if A, then C. If I study hard, then I will go to college. So I can use those, put them together, and drop out that middle term. So down here we're going to talk about reasoning. Tell whether the following examples of inductive or deductive reasoning. So all men are mortal. Harold is a man. Therefore, Harold is mortal. That is deductive. We're using a general case. All men are mortal. We're applying it to a specific case. Harold is a man. We're going to use that general reasoning to say, therefore, Harold is mortal. The coin I pulled from the bag is a penny. A second coin pulled is a penny. The third coin pulled is a penny. Therefore, all the coins in the bag are pennies. That one is inductive. We're using an experimental approach. And we're saying, all right, I'm going to take this information that I know specifically, and I'm going to draw a more general conclusion. You might be thinking, well, that's not necessarily true. There could be other coins in the bag, and you are right. So reasoning doesn't have to be true, but it can still be inductive or deductive. If a reasoning is not true, if it doesn't make sense, we say that that reasoning is not deducible. All right, not deducible. So we want to say that deductive and deducible are sort of different concepts. So deductive and deducible don't really have the same meaning. Deductive means, is it general to specific logic? And deducible means, can you show that that's true? Can you prove it? So this one is not deducible because it's not necessarily true. A shape has four sides. Shapes with four sides are called quadrilaterals. Therefore, the shape is a quadrilateral. This one is deductive reasoning. We're using the general shapes with four sides are called quadrilaterals and applying it to the specific shape that has four sides and drawing a conclusion from there. And then all students eat pizza. Emily is a student at Fullerton College. Therefore, Emily eats pizza. Again, that is deductive reasoning. Right? We're using the general case that all students eat pizza. We're taking that and applying it to Emily, who is a student at Fullerton College, and concluding that therefore Emily eats pizza. Right down here, we're going to identify the hypothesis and the conclusion of each conditional statement. So the hypothesis of the statement is the if portion. The conclusion is the then portion. So if we say if a point is the midpoint of a segment, then we're going to use that as the hypothesis, because it comes after the word if in the sentence. Then the point divides the segment into two congruent segments. That is the conclusion, the then. we always want to assume the hypothesis. That means that we want to say that this first part has to be correct, or else there's no reason to use this conditional statement if the first part's not correct. A student is passing if they have a score of 60% or higher. In this statement, they have a score of 60% or higher is the hypothesis, because although it's at the end of the sentence, it still comes after the word if. So we have to assume a student has a score of 60% or higher, then we can say they are passing. So the conclusion is the student is passing. Next, we want to talk about negation, and this is one of the main things we're going to be talking about today. So negation is how to take a statement and manipulate it so it says the opposite thing or the reverse thing. We're going to take that statement, we're going to see if we can use it if we flip it around to try and make the logic work differently for us. So our statement symbolically is going to be if A, then B. If A happens, then B happens. The converse of that statement is what you get when you flip those two things around. So instead of if A, then B, the converse is going to be if B, then A. The inverse takes a statement and it applies the word not. So instead of assuming the hypothesis is true, we're going to assume that the hypothesis is false. So we're going to write if not A, then not B. So if the hypothesis is false, then the conclusion is also false. All right, and then a contrapositive is the combination of the converse and the inverse. So we're going to reverse our statement and apply the word not. So the contrapositive of the statement if A, then B is if not A, if not B, then not A. All right, so that can get a little bit confusing. We're going to apply it to some situations and you're going to see what makes more sense. So coming over here, we have write the converse, inverse, and contrapositive of each statement, then tell whether the resulting statement is true or false. So we're going to talk about the truth values of these statements. Are all of the negations of these statements true or are they false? Are they not going to be true for you? So the first one, if an angle contains 90 degrees, it is a right angle. We could write then it is a right angle if we wanted to, but we don't need the word then. But we're going to assume this is true. We have to start with a true statement or else all of our negations don't mean anything. The converse of this statement is if an angle is a right angle, then it is 90 degrees. All right, so we can use grammar to make these sentences grammatically correct when we switch them around. We don't need to make the wording exactly the opposite as long as we keep the spirit of this and we flip around the hypothesis and the conclusion, right? We still want an if-then statement, though. We don't want a then-if statement. So if an angle is a right angle, then it is 90 degrees. Well, that statement is also true. What about the inverse of the original statement? So here's the original. The inverse is if an angle is not 90 degrees, then it is not a right angle. And when you think about that statement, think about whether it's true or not, and that is indeed also a true statement. If an angle is not 90 degrees, then it can't be a right angle. And then finally, we've got the contrapositive of the statement. So the contrapositive combines the converse and the inverse, and we can say, if an angle is not a right angle, then it is not 90 degrees. And we think, well, is that a true statement or not? And that is indeed a true statement. If it's not a right angle, then it can't possibly be 90 degrees. All right, so in this case, the converse, the inverse, and the contrapositive, they're all true statements. But is that always going to be true? We're going to see. Here's a new one. If Mary received a B on her test, then she passed the test. That is the true statement. The converse of that statement would be if Mary passed the test, then she received a B. Now, is that true? That's not true. That's false. Because if Mary passed the test, she didn't necessarily receive a B. She could have received other grades as well. What about the inverse here? The inverse would be if Mary did not receive a B on her test, then she did not pass. Then she did not pass. Well, is that true? Think about that. That one's false as well. Because if Mary didn't receive a B on her test, that doesn't mean she didn't receive some other kind of passing grade. So that one's a false statement. And then finally, the contrapositive. If Mary did not pass the test, then she did not receive a B. And we say, well, is that true? That one is true, because if she didn't pass the test, there's no way she could have gotten a B on the test. So what we want to do is we want to draw a conclusion about the truthfulness of converse, inverse, and contrapositive statements. So if a statement is true, then its converse is sometimes true. Sometimes it's true, sometimes it's false. We always have to check. If a statement is true, its inverse is sometimes true, right? But if a statement is true, then its contrapositive is always true. And I know we didn't do enough examples to say, oh, it's always true all the time, but I'm just going to tell you that. That one is for sure. If a statement is true, then its contrapositive is always true. So the next thing we want to do is just a quick example of the chain rule. Draw a conclusion from the following statements. If you study hard, you will earn a good grade. If you earn a good grade, then your family will be happy. There's two if-then statements here. A to B, B to C, right? B to C. So it goes from one hypothesis to a conclusion, and then that same conclusion turns into the hypothesis and then goes to another conclusion. So we can just drop out that middle part altogether, and we can say, if you study hard, then your family will be happy. So we know there's another step there. We just didn't write it down because we didn't need to. We just assume that step. All right, down here in these practice together, we're going to skip this one because it's just another inverse, converse, contrapositive. But down here I want to talk about this. Turn this into a conditional statement. Isosceles triangles have two sides with the same length. We need to turn that into an if-then statement. We can do this a few different ways. We just want to think about the two parts here. Isosceles triangles have two sides with the same length. So this is a sentence that's talking about isosceles triangles, and it's saying something about them. It's saying they have two sides the same length. So what we need to do is give one of these an if and one of them a then, and we're going to need to make it into a grammatically correct sentence. So we can say, if a triangle is isosceles, then it has two sides with the same length. Now, that's not the only conditional statement we could use here. We could say that if a triangle has two sides the same length, then it is isosceles. And we could move around the grammar and make that say a few different other ways of saying, but as long as we have it a hypothesis of an isosceles triangle and a conclusion of the triangle having two sides the same, or if we have a hypothesis of the triangle with two sides the same and a conclusion that that triangle must be isosceles, then this works as a conditional statement.